And it's recording. Here we go. Exercise 13D. So this is now assuming that you have practiced some index laws. So 13A and B. C you don't really need. So if you're pressed for time, I want you to work on A, B, and then D. Yeah. C is sketching, but with D, you're able to sketch it properly. So axis, intercepts, and all that. So if you're struggling algebraically, I'd say stick to A, B, and then practice with D as well. Okay, C is for conceptual. So let's start off here. So we're now solving exponential equations. So you've learned how to simplify through 8 index laws. And now, is there a spare over there? No? Molly. There's 2 there. Just grab one. Now we're applying the 8 index laws to solve different situations. Let's try this one. So here's the logic. And I know one of the reasons why students find exponentials and logarithms hard is because you're used to seeing, and try to follow me here. I'm going to highlight the colors for you to understand. Yeah, that should be the right one. You are used to seeing the operations, which I'm coloring in yellow. I'm going to call it operations. So operations. You're used to seeing a symbol for it. And then there's a value or quantity that's attached to it. Okay, so I'm going to do it in blue, value. In blue. So you're always used to, there is an operation and then a value. So when we did algebra, we always said, well, what is the opposite of, for example, this case? At year 7, you learned not to use trial and error and guess the number to be 5. Okay, instead of guessing it, we teach you inverse operations. So we say, what's the inverse of plus? And you would say minus, right? So you got a symbol again. So you're used to saying, yeah, opposite of plus, minus. And then, well, how much are you adding on? I'm adding on 3. That's the quantity, that's the value. So then when you minus, well, you do exactly the same. You say then it's minus 3. Now, balancing the equation, we know whatever you do to one side, you do to the other. It might be.
Yeah, 13.
Sorry, maybe it was this one. Did it say 5B on it or something?
No, it's just 13.
Oh, that's last session. Sorry, my bad. I think it's that one there. Find the one that... Oh, yeah, it's right on my pink folder. Did you get the right one?
Yeah.
13D?
Yeah.
Okay. All right, so whatever you do to one side, if you minus 3 on one side, then we learn to balance the equation. We say minus 3 on the other. That was the logic, yeah? Because whatever you do to one side, you have to do to the other. And the reason for that, very logically, if I had $3 in my pocket, I still have $3 in my pocket. But if someone gave me an extra $1, so I add an extra $1 to one side, and I don't do it to the right side, it's not true. So the statement is only true if whatever you do to one side, you do to the other. That's the reasoning to what you did in year 7, right? So, same thing here, minus 3, we can then say minus 3 and plus 3 cancels out to be 0, and then you work out what 8 take away 3 is, and so then you say, therefore x must equal to 5. Now let's do the same thing for times. Opposite of times is divide. So then you would say, divide the left-hand side by 4, and then divide the right-hand side by 4. And the same concept happens again. 4 divided by 4 is not 0. 4 divided by 4 is 1. They're inverses of one another again. So they cancel out to be 1, but then x times 1 gives you x. Just like this one, positive 3 take away 3 is 0, and x plus 0 still gives you x. That's why the left side is always x, yeah? So far, this makes sense. A lot of students get it. It almost becomes intuitive now. For year 7s, 8, it's not intuitive. For you guys now, it would be. But what's not intuitive is then when you get to exponentials, can you see the difference? There is no more operations. You got a value though. You're saying 3 to the power of x equals 9. Your problem here is you still need the same thing. You need x equals to something. Now you can use your year 7 knowledge and do exactly what year 7s would do. You would do it intuitively. If I said 3 to the power of what will give you 9? What would you say? 2. Because you're doing exactly what year 7s do here, where they say 5 plus 3 is 8. I'm like, great. I'm like, well, how'd you do it? They're like, because I just know it. Well, same thing here. You would just say, I just know it's 2. So the problem right now is you've got the value of 3, but where is the operation? Where's the symbol? And because there's no symbol, this is the reason why when you guys learn logarithms and exponentials that are opposites of one another, why it becomes tricky. Okay, it's more of a visual problem, less so conceptually. Conceptually, it's exactly the same. It's just that there's no operation. The operation in itself is actually the positioning. That's the operation. The operation is actually the positioning of the x. By moving the x into that position, that is the operation. That's why it just feels weird. Yeah? But later on, once we learn logarithms, I'm going to come back to this concept so you understand. So now, yes, I do know the answer is 2, but I don't actually have a technique. Notice that there is no technique at the moment. Unlike these ones, there was a technique. So how do you solve it then? If there is no technique, how do we solve for 13D without using logarithms? Well, the only other way is what we do. Since we haven't learnt, fill this in, logarithms, which is the opposite of exponentials, then we're going to have to use another approach, which is called by inspection. You're solving by inspection. So if you ever see a question or YouTubers say solving by inspection, this is what they mean. Let's have a look at this equation. Doesn't take a genius to figure out this one. You can do it intuitively because maths is logical, right? If I told you in this expression on the left is a squared plus b to the power of 5 plus 3 is equal to, meaning it's exactly the same as a squared plus something plus 3. What goes in that little missing space? What goes into the gap? B. Now you knew that without thinking. This is called by inspection because you're looking on the left-hand side. You say, do I have an a squared? Yes, I do. You're looking on the left-hand side. You're like, oh, I've got a 3. So they've got a 3 as well. But since they're equal, logically, this has to be this. So this is what we're going to do with exponentials. We're going to do exactly the same skill. We're not going to use logarithms, but we're going to solve by inspection. So to do by inspection, you first need both the layouts on either side have to look exactly the same in every single way. Okay, it has to look exactly the same for you to inspect it. So right now, I've got 3 to the power of x, but this side is a fraction. It does not look the same. So what we're going to do is we're going to use our index laws to try to figure out this problem. So this has a 3, that has a 9. That's a problem already. So let's make the 9 a 3. What's 3 to the power of what to give you 9 again? Let's say 2. So then I can rewrite this as now, this is 3 to the x is equal to 1 over 3 squared. Now we're getting closer. They both have a 3. But 1 is not a fraction. 1 is a fraction. There was an index law that you've learnt already since year 7 to now, or technically year 8 and 9. Which rule can I use to change this not to a fraction anymore? Which rule was it again? You might not know the number, but you can tell me what rule it is. It's number 7. But what were you thinking? What's the rule? Very good. So that's rule number 7. It's the one with a to the power of negative m is the same thing as 1 over a to the power of m. Yeah, so you change from a negative power to a positive power. Right now it's a positive power. So you can actually write rule number 7. So I'm going to write here rule 7. Rule 6 is the power of 0. So here it's 3 to the x is equal to 3 to the negative 2. That's rule number 7. Now they look very much the same. They both have a 3. They both have a power. So if I'm saying, what is x, just by inspection, I can already say, well, they both have a 3, so that's ticked off. The only part I don't know is x, but x is the power. So you can now say, by inspection, x must equal to negative 2. Does that make sense? Yeah, so your skill in all of these examples is try to do it by inspection. There is no solving with logarithms. You're trying to make it both sides look exactly the same. Okay? Let's try the next one. So this one is a typical year 9 question. Let's move on to that. That's about a year 10 question now. So let's have a look at the year 10 question. All right. So what do we have on this side? We have 5. That's not a 5. That's 25. You can't do the comparison. You can't do inspection. So you're going to change them. Here we go. So this is 5 to the power of 3x minus 1. How can I rewrite 25? Let's go with Zoe. How can I rewrite 25? 5 squared. So this is now 5 squared, which is 25. But then it's 25 to the power of x. So another way of writing it is 5 squared to the power of x. See that? And the reason why I put the brackets is because you have to be clear. Because later on when you get more different powers, the brackets matter. Yeah? So I put in the brackets so that you don't jump from 25 to the power of x to 5 to the power of 2x. Don't do that. Okay? Because if I change it to minus 1, you have to put in the brackets to make sure you're not going to make a mistake. Yeah? So get in the habit of putting brackets in. Because 5 squared gives you that 25. And then from that 25, you do to the power of x. So that's why I'm doing that. Yeah? Now, rule number what? Or what's the rule that you can get rid of those brackets there? What was the rule again? You might not know the number, but you know what technique it is. 3, very good. 3 tells you that you multiply, or you can multiply the powers together. So this now gives you 5 to the power of 3x minus 1 is equal to 5 to the power of 2 times x, which is 5 to the 2x. Yeah? So now what you can say is both sides of the equation have a 5. So that's ticked off. That means both powers, since they're both equal, the powers must be the same as well. Whatever's here must equal to that. Whatever's here is equal to that. That's what we're doing. We're just doing by comparison. So therefore, I can say 3x minus 1 must equal to 2 times x. And now you got an equation that is possible to solve, because all we're doing is by inspection. There is no actual inverse operations that you're doing right now. Yeah? From here, solving for this is just a linear equation. So here we go. Let's minus 2x on both sides. 2x take away 2x cancels out, and 3x take away 2x is now 1x. So therefore, x is equal to 1. I'm just going to put a negative there so it looks clear. So far, so good. That's example 2. Let's move on to a bit harder one now. So can you see I'm moving from simple year 9 to just a bit more tricky, because both powers have now an expression in it, to now, again, still year 10, but with fractions, because students hate fractions. Let's try this one now. I want to pause the video. 3, 2, 1. Let's check our answers. So, first part. I checked the numbers. I can see there's a 5, 25, and 125. So I just made sure I changed them all so they're all the same. 125 is 5 cubed. 25 is 5 squared. Notice I put the brackets in. Brackets matter. Because if you don't put in the brackets, the mistake is that you don't multiply 2 to the negative 3 as well. If you just wrote 5 squared and then wrote n minus 3, you would have just had 2n minus 3. That's where the mistake comes in. So make sure to put the brackets so you know it's 2 times the negative 3 as well. So next one. I skipped a step. Well, not really. I just combined it all in one. So here, it's times the power, so 2 times n minus 3. And then here I use rule number 2. Rule number 2, you say same bases, subtract the powers. So this is what I did. I literally wrote 3n minus 3, take away 2 times n minus 3. So I did it all in one line, because that's rule number 2. Rule number 2 just says a to the power of m divided by a to the power of n. You take away the powers. You see, what I did all in one step, I still kept the brackets, and I kept that minus sign. So you can see here the common mistake that students make. It's right there. That negative 2, if you don't use the brackets, you would then do negative 2 and you don't times by negative 3, you'll get it minus 6. Can you get a show of hands who got a plus 6 correctly? Oh, no one got it. 1. Okay, good. Well, that's one thing to pay attention if you got that wrong. Yeah, so that there, a lot of students will write minus 6. And that comes with poor layout. It will happen all the time. It's not a mistake. That's a habit. A habit you got to fix. Yeah, so it's the way you write your thinking. That's where the mistake comes in. Okay, so negative 2 times n is negative 2n. Negative 2 times negative 3 is positive 6. If you do that correctly, well then 3n take away 2n is n. Negative 3 plus 6 is 3. Now the bases are the same. That means the powers must be the same. So n plus 3 equals 3. And if you work it out, n should equal to 0. Can I get a show of hands who got n equals 0? 1, 2, 3, 4. All right, good. Oh, good. It's a pretty good ratio. As in, like, it was a tricky question. But that's year 10 still. That's not really year 11 yet. That's your year 10 algebra that you should be practicing. There you go. Let's look at the second example, but I modified this. Same idea. This one should be easier. Just be careful with your powers and negatives. I'm going to pause again in the video. Here we go. Did we get n equals 5? Hands up if you got n equals 5. Okay, good. Better ratio. Excellent. Again, same thing again. Just keep, I noticed that 64 can be written as 4 cubed. Bring it up using rule 7. Powers must be the same. Added n, added 3 on both sides, and then n equals 5. Okay? All right. Let's flip over and let's start some year 11 techniques now. Flip over the page. Remember, all these notes are on OneNote, so if I'm going a bit too fast, you can go back and watch the video or look at my notes again. Let's start off here. So this is a beginning of a year 11 type questions. It's exercise 13D, question 3A. So let's have a go. Same idea. So I'm going to write now 2 to the power of x minus 1 times, I'd say 2 squared. Notice I'm putting the brackets in. 2x plus 1. And that's 2 to the power 5. Together, rule number 1 says you can add the powers together. So it becomes x minus 1 plus 2 times 2x plus 1. Since the bases are the same, that means the powers must be the same. So you should now have, therefore, x minus 1 plus, I guess if you expand it, 2 times 2x and 2 times 1, that's 4x plus 2 is equal to 5. That means 5x plus 1 is equal to 5. And doing a bit of a quick maths here, 5x, that's 4, and x equals to 4 over 5. So far, so good. Okay, so those are the type of questions that you'll practice at 2 and 3, just building in your year 10 knowledge. Obviously, there'll be some with fractions as well, so just making sure you've learned your year 10 algebra. But the next question, a very typical year 12 exam question as well from exam 1. I'm going to pause this video for you to think about, and I'll give you a hint though. Let's do the answers. So, where's the little trick? Here's the trick. 2 to the x. That's one of the things that is confusing at the moment. So what you do is you rewrite this to have 2 to the x in it. See, at the moment, this is like 2 to the power of 2 times x. That is the same thing as saying 2 to squared x. But that 2 times x doesn't have to be 2 times x. You can write it the other way around. You can write it as 2 to the x, all squared. And by rule number 3, still the same thing. X times 2, or 2 times x is the same thing. Now when you do it like this, why would I want to write it like that? Because you now have 8 bracket 2 to the x squared, take away 10 bracket 2 to the x plus 2, it's all equal to 0. Now for some of us, this still looks confusing. But if I highlight it, see that? If you gave it a letter, if it makes it easier for you, if you just said something like, let a equal to 2 to the x, suddenly you change your problem into a quadratic problem by having 8a squared, take away 10a plus 2. See what I've done there? All I've done is I've changed something that looks a bit intimidating and a bit confusing to something a bit more familiar. Okay, and the tip is right there. So you see that little square? That 2 times x doesn't have to be 2 times x, it could be the other way around. It could be 2 to the power of x squared. 2 to the power of x squared is still the same as 2 times x or x times 2. Okay, so once you've done that, it's about quadratics, factorizing. I would probably divide them all by, they all have a common factor of 2. So if you divide them all by 2, you get 4a squared minus 5a plus 1. So if I divide this by 2, divide by 2, divide by 2, divide by 2, divide by 2. Let's refresh your memory on quadratics. Has anyone figured out the 2 factors? And we factorize that. I'll move it up a bit so you can see. Oh, what happened? Whoops, sorry. Here we go. Anyone got the brackets? Hands up if you got it. If not, I'll write the answer. No one? All right, let's factorize. So clearly it's a 1 and a 1, so you can't really do much there. Let's see, 4a, I would do 4a, and minus 4a and minus 1 could give me minus 5, and double negatives positive. Yep, there we go. So I factorized it. So again, if you don't know how to go from this step to this step, this is chapter 3. You still have to revise that. That's a prerequisite by this point. Okay? That's 3C, I think it is. 3C and 3D. So you have to go back and revise if you've forgotten how to do that. 3C, 3D from chapter 3. So I factorized it using null factor law from 3D. What does A equal to? A equals to 1 over 4 and 1. But that's not my answer, because remember, I made up A. I said let A equal to 2 to the x. So you now have to actually answer the question. Well, if A equals 2 to the x, then you have 2 to the x equals 1/4, or 2 to the x equals to 1. Now, just on this side, 2 to the power of what? What would x have to be to equal to 1? No. Think about it. 8 rules. There's only one rule. 0. Remember, anything to the power of 0 is 1. So, right there, x has to be 0. Because rule number 6, that's rule number 6. So rule 6, that's why you need to know all the rules. 8 rules, you're going to be very fluent with them. Next one, rule number 7. This one's rule 7. Bring the 4 up. And that's the same thing as writing 2 to the x is equal to 2 to the power of negative 2. Okay, because 4 is 2 squared. But if it's in the denominator, you can bring it up using rule 7. And therefore, x equals negative 2. In year 12, when you're solving for it, you'll have to realize that sometimes, depending on the problem, you can't have negative answer. In this case, it's fine. You can have both answers. But that's a typical year 12 exam 1 question that they sometimes chuck in. Maybe question 4 or 5. It's worth 2 marks. If it's a justification question where you have to discard one of them because it doesn't make sense or it's not valid, then that's 3-mark question. That's 3 out of 40 marks, which is a lot of percent for exam 1 question, which you guys have already learnt. Okay, so practice that one. That's a typical one if they want to spiff it up. 13D, question 4. Have a look at that. There's only like 4 questions, I think, for you to practice. So if you want more, I can come up with more. Or find some year 12 exams. Yeah? All right, let's have a look. These are 2 year 12 exam questions for you to try. That's 2011. Exam 1, question 2B, worth 3 marks. Use the technique I just showed you. Have a go with this one. This one should be less. This was surprising. Back in 2014, they still assessed a Year 9 question. So have a go. You could get 2 marks out of 40 at the time. But that was back in 2014. Yeah? I want to pause the video. Let's check your answers. So VCAR 2014. Let's see how many people got 2 marks if you were doing exams in 2014. Here we go. First one, change the 8. Well, sorry. Change the 8. Get a base 2. The only mistake that students make and why it was in the exam is because examiners know students screw up right that step. So hopefully this time you've learnt the brackets, you're not going to make that mistake, and you actually ended up with minus 3x. Can I get a show of hands who got that minus 3x? Good, because that's what the examiners were doing. They did it on purpose, and in that year, or previous years, students suck at their algebra. That's why that was in there. Now it's not a problem, so you're going to get harder ones than this. So, solve them. Powers must be the same. So 3x minus 3 equals 6 minus 3x. And therefore, x equals 3 on 2. Make sure to simplify your fractions. They only accept one answer. There is not multiple answers. You leave it as 9 on 6, you lose a mark. Has to be 3 on 2. Can I get a show of hands who got 3 on 2? Good. Excellent. You got yourselves 2 marks out of 40 in 2014. All right, 2011. Here we go. Turn them into quadratics. First step. Shh. Listening? Thanks. All right, here we go. The second one. The hint is looking at the exponential. That's 2 to the x. Notice what I did at the first step. I got rid of the 16 by minus 16 on both sides. Because I know it's going to be quadratic. Having a 0, you can use null factor law later. Next step is to convert. Is convert that 4 to the x into 2 to the x. How can you make that? So I changed the 4 to 2 squared, and just like before, 2 times x doesn't have to be in that order. It doesn't have to be 2 times x. It could be x times 2. So I flipped it around, and now what you can see is 2 to the x squared, and this is 2 to the x. If you still can't see it at this point that it's quadratic, it might help by saying let a equal to 2 to the x. So if you let it equal to a variable, it's easier to see. So I just replaced that with an a, so it becomes a squared minus 15a minus 16 equals 0. From that step, chapter 3, factorize exercise 3c and 3d. Factorize it, and then when you solve it, you should get a equals -1 or 16. Can I get a show of hands who got up to this step and got it correct? Okay, so that's 2 out of 3 marks so far. So up until this point, you would get 2 marks for 1, constructing the equation, 2, getting the correct possible answers. Then the third mark, the reason why it's a 3 marker is one of these answers is not possible. And if you wrote it out clearly, A was meant to be 2 to the x, right? So I'm going to just bring it up a bit. A is equal to 2 to the x. So 2 to the x could equal to -1, or 2 to the power of x could equal to 16. Now clearly, 2 to the power of 4 will give you 16, so x can equal to 4. This one though, examiners want to know that you know that is not possible. And that's how we know if you understood what exponentials are. So if you think about what I taught you last session, see 2 to the x. Remember I taught you the graph? If you visualize it, 2 to the x looks something like this. Has an asymptote, so it never equals to 0. It crosses through 0, 1. If it's a base of 2, it means every time you go to the right on the positive side, it doubles. So it goes 2, 4, 8, 16, 32, onwards, right? So it keeps going up. So it can't be negative. We're trying to get -1 at the moment. We're asking, when is this graph equal to -1? But even just looking at the graph already, -1's down here. There is no way the graph is ever going to touch that point because there's a limit. It's already said that y has to be, it can't be 0. So it's never going to be negative. But on the other logical sense is, you go to the right, it doubles, but when you go to the left, it halves. It goes 1/2, 1/4, 1 out of 8, 1 out of 16, and 1 out of 32. So it only gets smaller. It never actually becomes negative. So all exponential functions, one of the first properties that you should have, is can't be negative. That's one of the first things that you need to know. And that's what they want. So you have to say something like this. 2 to the x, or you can say x is undefined. Because 2 to the x is greater than 0. That's how you get your third mark. So you need to show to examiners that you know 2 to the x cannot be a negative value. You can say it's undefined. I like to add in the extra word or sentence to say 2 to the x is always positive for all x values. No. If you just did the other answer and without justification of any form of saying it's undefined or 2 to the x is greater than 0 for all x values, then they assume that you just didn't like negative numbers and picked positive numbers, but you don't truly understand why. So you wouldn't have gotten the third mark. So third mark is a justification mark, and it has to be done that way to get full 3 marks. Okay? All right, team. So that, if you want more practice of that, that's question 4 of exercise 13D. Last one. This is now inequalities. And again, the better you understand the graphs, the better you can answer this question. So I tried to help you visually here. I don't actually know what 4 to the 2x plus 1 looks like perfectly, but I do know one thing. It has no vertical translation, doesn't go up or down, but it might move left or right. Right? But that doesn't matter because asymptote is still 0, never touches 0, and it's positive. So that means it must be like this. When you say, when is 4 to the 2x plus 1 greater than 64? This is what you're actually asking. You're asking, when is this graph greater than when y is 64? See, that's 64 there. So there must be 4 to the power of something eventually equals to 64. I'm asking, when is it greater than? So the region that I want is all from here onwards is when the graph is greater than 64. From here below, this is when the graph is less than 64. Okay? So the question was asking, what x values will the graph be greater than 64? Well, I need to find this point to begin with. I need to know what x value at that point to equal to 64. Then I can say anything greater than that value will be greater than 64. So how do you find that point? Well, instead of a greater than, I'll say, when does it equal to 64? So 4 to the 2x plus 1, when does it equal to 64? Now we can solve it again. 2x plus 1 equals 3. Then x equals 1. So what this means, x has to equal to 1. That's when it will equal to 64. But I don't want 2x plus 1 to equal to 64. I want it to be greater than. So it has to be this side. What's my answer for the question? X needs to be bigger than 1. So any number bigger than 1, if you did x 1.1 or 1.01, it will be bigger than 64. So here's your answer. X needs to be greater than 1. When you're dealing with inequalities, please draw the graph. Don't try to do it algebraically alone. Try to visualize it. That's what methods is about. It's about analysis. Okay, so you have to understand the graph well. So that's why it links with 13C. So 13AB is your algebra. 13C is the visualization. 13D is solving without using logarithms yet. Okay, you tie those two together. That's a bit of mostly year 10 stuff and a bit of year 11 context. Okay, that's when you want to build before you do logarithms next week. Okay, so next week is logarithms, but I need you to have strong algebra on exponents first. Okay, I'll stop the video there, and the rest of the time is yours. About 20 minutes. Stop the video.